Hello students, as we have discussed in last lecture, okay, I am showing you the summary of the Bode magnitude and phase plot. Okay, so see, all these are the factors from the transfer function that we have already discussed in first lecture. So see how many factors are there. Factor number 1, constant gain k, then pole at origin, number 3, 0 at origin, first order pole, it will be the real pole. Then number 5, first order 0, that is real 0. Then number 6 will be the second order pole, okay, just like the quadratic equation. Then number 7, second order 0, okay. So there can be the maximum of 7 factors present in any transfer function, okay. So transfer function may vary. So how you will calculate the magnitude and the phase plot, okay. For that, look at this first factor. So this column is for the factors, then here actually magnitude is shown and this is actually the angle, okay. So look at this first factor I have considered as constant gain k. It will be always there in any transfer function. So 20 log k, okay. We already derived this magnitude and angle in last lecture, okay. So directly I am writing here 20 log k. It will be always to the base 10. I am not writing to the base 10, so it is understood that we are considering decade. So angle, it will be 0 degree for any constant value. Then next, pole at origin 1 by j omega raised to power n. So this is the generalized form, n number of poles are there, okay. So we have calculated the magnitude and angle in last lecture and I have shown you how to draw the magnitude and angle on the Bode plot, okay. So look at this. What will be the line slope you will be getting? Straight line at minus 20 dB per decade, okay. So when there is a pole at origin, one pole at origin, so line slope it will be always minus 20 dB per decade, okay. So line slope passes through omega is equal to 0 degree, okay. So I have shown you how to draw the line for minus 20 dB per decade, okay. Then next, 0 at origin, so generalized form again I have taken j omega raised to power m. So for 1 0 it will contribute to line slope of plus 20 dB per decade. Look at this. For pole it is minus 20 dB per decade. Angle is minus 90 into n. One pole will contribute minus 90. So it will be always multiplied with the number of pole. Here it is multiplied with number of zeros. So I should write here m. Okay, because here I have taken m. So next, first order pole. So this is a finite pole, just like s plus a form in the denominator. Okay. So this S plus A form, just imagine S plus A form is there that I have arranged in the standard transfer function of the Bode. So 1 plus j omega by P1, okay. So look at this. This is actually first order pole. So now the line slope will be divided into two parts, okay. Why it will be divided into two parts? Because this omega by P1, it will be having two values. It depends on the value of P1, okay. For omega less than P1, your line slope will be different. For omega greater than P1, your line slope will be different. Please understand. When the pole or the 0 are at origin, you are getting a single line slope. But when such thing is there, so for such real pole or 0, there will be always a corner frequency. Okay. What is corner frequency? That omega by omega n term is there. When we are arranging the transfer function, we are getting omega by something. Look at this. This part it will be in the denominator. So this part is called as a corner frequency. Okay. So your line slope is always changing at line corner frequency. So before corner frequency, line slope will be different. After corner frequency, line slope will be different. So here actually look at this, line slopes are there. So what I have written, 0 dB per decade for omega less than P1, okay. For omega less than P1, okay. So before this P1, you will be getting a line slope of 0 dB per decade, okay. Then next, look at this. Here I told you that one pole is contributing to line slope of minus 20 dB per decade, okay. So above this, for omega greater than P1, there will be the line slope minus 20 dB per decade. But here you know that you are getting directly minus 20 dB per decade for the pole, or for 0 it will be plus 20. So what you will calculate the angle? Angle it will be, look at this here, this part is in the denominator. So angle it will be always negative. So minus tan inverse of B by A. So omega by P1 upon 1. This will be your angle. Okay, so next, first order 0. Look at this again, here finite 0 is there in the numerator part. So 1 plus j omega by z1. Okay, so line slopes are number 1. Again, it depends on the value of z1 for omega less than z1 and for omega greater than z1. Okay, so line slope it will be 0 dB per decade for omega less than z1. Okay, then it will be plus 20 because 0 is there. 1 0 is contributing to line slope of plus 20. So plus 20 dB per decade is there for omega greater than z1. Look at the same thing we are doing. This is for only finite poles and zeros. Okay. So what about the angle? Angle is actually b by a, tan inverse of b by a. So this angle it will be always positive for the 0. So phi is equal to tan inverse of omega by z1 upon 1. Okay. I hope you are getting this table. Then there will always be the possibility that quadratic pole may be there, poles may be there, or quadratic zeros may be there. Okay, so we know that the second order standard characteristic equation is given as s square plus 2 zeta omega ns plus omega n square. So this is actually the quadratic form where omega n, you know that this is actually the natural frequency of oscillation. Omega n is actually natural frequency of oscillation. So this function or equation, it may be in the numerator or it may be in the denominator. So look at this, second order pole is there. So this is in the denominator form and this equation is arranged in standard Bode form. So what is actually the standard Bode form? You will get one thing that I have arranged the transfer function in such a way that the real part and imaginary part can be directly taken out. Okay, so look at this, here actually I have divided this with omega n square, the complete equation. First of all you need to put s is equal to j omega, then you can rearrange. Okay, so the important thing here, second order means highest power of s in denominator is 2. Okay, so two poles are there. One pole is contributing to line slope of minus 20. So two poles it will be contributing to line slope of minus 40. Again the same thing is there. Look at this. This is actually your corner frequency. Whatever I have shown here omega n, this will give you the corner frequency. So again the Bode plot, it will get divided into two parts, before omega n, after omega n. So look at this, line slopes are 0 dB per decade for omega less than omega n. And it will be minus 40 because two poles are there. So minus 40 dB per decade for omega greater than omega n. Okay. Again the same thing, you can calculate angle, as this is in the denominator part, angle it will be minus. So minus tan inverse of, look at this, b by a means imaginary part upon real part. So this imaginary part is zeta omega by omega n and real part is 1 minus omega square by omega n square. So I hope you are getting. Then the last factor is second order 0, same thing. Okay, suppose this equation is there in the numerator. So 1 plus 2j zeta omega by omega n minus omega square by omega n square. So this will be my corner frequency. So again the Bode plot is divided into two parts, before corner frequency, after corner frequency. So two zeros are there. One zero is contributing to plus 20 dB per decade. So two zeros will be contributing to minus 40 dB per decade. Two zeros will be contributing to plus 40 dB per decade. Okay. So line slopes are, look at this, here 0 dB per decade for omega less than omega n and plus 40 dB per decade for omega greater than omega n. Okay. And the same thing you can calculate for 0 angle, it will be always positive. So phi is equal to tan inverse of b by imaginary part upon the real part. Okay, so this is about the summary of Bode magnitude and phase plot. Okay, in next lecture we will directly start the procedure and we will check what is gain margin and phase margin. Thank you students.